Hello and welcome to another video. In this video we're going to be working on dividing an array into subarrays with minimum cost 1. And this is going to be the first problem of the Biweekly Contest 122, and I think it's hard enough to do a video on it, especially to get the optimal solution. So it's a pretty straightforward problem. You're given an array and you need to divide it into 3 contiguous subarrays, and the cost of each subarray is just the first element in the subarray. So for example here, for 1, 2, 3, 2, you can divide it like this: 1, 2, 3, and 12. And the cost of all of this is 1 plus 2 plus 3, because you just take the first element of every subarray and you add it together. And there's other ways to divide it, but those are worse. 5, 4, 3, there's only 3 elements, so you just have to divide them into subarrays of length 1. And in this last example, the best way is 10, 3, 1, 1. And obviously the constraint is really small, so let's talk about a brute force first. So let's just say we have this kind of problem. So we know that the first subarray has to start at the first element, right? There's nothing we can do about that. Like, this just has to start here. But the second subarray can start anywhere, and the third subarray can start anywhere. So let's use another color for the second subarray, right? And we'll just have an arrow for its start. So it obviously can't start like over here because we need 3 subarrays, but it can start here, 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 here. So a brute force would basically just be loop through this whole thing and just have like a nested loop. So just say like the second subarray will start at some number and then loop through every other index left and figure out where the third subarray will start, so you can have another something like this. So we'll have another color. So you say like, let's just try this, 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 and then get the minimum, right? So for example, this kind of situation would be the first subarray is this, the second subarray is this, and the third subarray is this whole thing. And that's kind of how you would do it. You would basically just say like, for a given start index of the second subarray, let's loop through all possible start indices of the third subarray. Then we'll move the second subarray index down to here and loop all these now, and then move it down here and loop all these, and then finally move it down here, and this will be the last one. And obviously the second subarray can't start here because then you need 3. So that's kind of how you do it. But notice that, like, let's say if we start here, like, where would be the best place to start the third subarray out of all these numbers, right? It's just going to be the minimum. Like, it's always going to be the minimum. So for 7, if we know which one of these is the minimum, then that's going to be the best place. So this is going to be the best result for these 2 numbers, right? Because then it's 8 plus 7 plus 2. Anything else would be bigger. So for a given index here, we know that we always just want to choose the minimum of whatever's to the right of it. And so that's going to be the intuition for this problem. Basically, for whatever index we have, as long as we know what the minimum number is of the elements to the right, we're always just going to choose that. So we can speed this up by keeping track of all the elements we've seen and storing the minimum. And it's going to be kind of hard to do it if you go this way. Like if we go here, let's say, then we're going to have to say like, okay, well, there's these elements over here, and like one of these is the minimum. Maybe we know it, but then if we go right, maybe we got rid of the minimum and so on, right? We want to be able to know the minimum in O of 1. So instead of going this way, we're actually going to go the other way. So we're going to start here, and now this third subarray will keep adding numbers. So then it's going to be really easy to keep track of a minimum. So we'll start here, and let's kind of walk through the solution. So for the third thing, let's have it as well. So right now this is just going to be our starting solution, which just has 9 plus 8, which is 17. Right? And this is going to be our current result. Then we are going to store the minimum up to all the numbers we've seen so far. So the minimum was here, but now that we're moving this back, now the minimum is this 4. So we're just going to store that number. And now for this index, the minimum is 4. So now our solution is going to be 14. Then we're going to store the minimum again. Is the current minimum, is the old minimum or the current value smaller? The current value is smaller. So we're going to store this number now. And this arrow isn't going to be an arrow, it's just going to be a stored number, right? It's more just this is the arrow we're traversing. So for this number now, what is our result? It is 8 plus 3 plus 2, which is 13. Then is the old minimum or the current minimum smaller? It's the old minimum, so we'll just leave that number as it is. Like I said, this will be just be a stored digit, not an arrow. And this will be our traversal. So this will be an O of n traversal. Then we go over here. And what's our result here? So it's 15 plus 2. Yeah, so it's just 17. And that's it, right? We can't, like, we're done. We can't go any more left. So basically, out of all these numbers, what's the smallest number? It's going to be 13. And we can just do this in place, right? We can just have a result that we just calculate in place. So basically, you just keep track of, like, what's the smallest minimum you've seen so far. And you keep updating it. And you want to go from right to left, because that way you will keep adding numbers to the minimum instead of removing. Because if you're going the other way, then you might have a minimum, but then you might have gotten rid of it. Like, let's say you're here and maybe you get rid of it, but maybe there's like 3 more 2s over here. How do I know, right? You can't. So that's why you want to start from here and you want to move backwards. That way it's very easy to just keep track of the current minimum. You just say, like, what's my current number, what's my old minimum, and let me store the minimum there. And the third array will always start at the like minimum you've seen so far, and then the second array will just loop from this number, the second to last number, all the way to the second to first number. We'll just loop and try everything, and that will be O of 1. And now we don't need to store any, we don't like have any space, and we have O of 1 or O of n time. So this can be the best way to do it. So we can code it. So we are going to store that like minimum last number thing. So we'll just first we'll make a length of the array. So for the default case, remember if we go back here, our default case will look like, we can actually have it here. This will be our starting stuff, right? So our minimum that we're going to store is going to be the last number, and we will start right over here, and we will loop all the way backwards. And we'll make result equal to infinity and try to minimize it. So we'll have our minimum be nums at n-1. And we will loop all the way from the second to last number to the second to first number. So for I in range, so we want the second to last number here, so this is going to be n-2, and we're going to go backwards, and we want the second to first number, or the second number, so this is just going to be 0, because it's not including 0, so it'll loop from n-2 to 1 backwards. So we want to just minimize the result, so we'll say result equals minimum of the old result, and we are including this current number that we're at as the start of the second array, and then the third number will be whatever our minimum was. So this is just going to be nums I, which will be the start of the second array. We're just trying every single location there in O of n, and this is going to be minimum. Then we update our minimum to be the minimum of the old minimum and the current index. So minimum equals min of, maybe not the best names, but it's okay, and nums I. And then finally, our result will basically have the smallest possible combination of the second and third value. And now we just return that plus the first value. The first value always starts at index 0, so we know it always starts there, right? The first array has to start at index 0. So we could say return result plus nums at index 0, which will be the first array. And we can submit. And there we go. And kind of strange. So I think when I ran it before, it was beating 100%. So I think it just depends. Like, it's kind of a small number, so it's just not very consistent. But yeah, this is basically going to be as good as you can do for this problem. So it's going to be O of n time, because we're essentially doing one loop backwards, and O of 1 space. And as always, for easy problems, you can always do them in like the brute force. That's like really easy. They give you super small constraints, so you can do this in like an n cubed or n squared or whatever you want, but it's still good practice to be able to do them in as efficient manner as you can. So to do this efficiently, I thought this was like difficult enough to go over. And yeah, it's gonna be all for this one, and then I'll do the next few today probably. I'm not gonna do like all of the contests in the next day or two, just because I had some other stuff I was doing. I actually had like a TikTok take home I was doing today, which was like 2 hours, so I don't want to do like 20 problems in a day. But I'll definitely do the problems for this contest and the next one in the next few days. So hopefully you guys did enjoy this one, and if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.